Hello everyone! In this digital signal processing and control engineering tutorial, we provide a clear and graphical explanation of the convolution operator, which is also known as the convolution sum or simply as convolution. Signal convolution is a fundamental operation in signal processing, control theory, machine learning, and time series prediction. Consequently, it is of paramount importance to understand the mechanism behind signal convolution and to understand how to compute signal convolution in MATLAB. All this is explained in this video tutorial. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as more than 400 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. The convolution operator is given by this infinite sum. And the best approach for understanding this sum is to try to write it down. So let's do it. Let n be a discrete time instant. And let x of n and h of n be two discrete time signals or discrete time sequences. Then the convolution of x of n and h of n is defined by this sum. Y of n is the sequence that's the result of convolution. It's equal to sum, where k goes from minus infinity to plus infinity, of x of k multiplying h of n minus k. Often in literature you will find that the convolution sum is written like this. Y of n is equal to x of n star h of n. That is, the star operator denotes convolution. In the theory of discrete time dynamical systems, the signal h of n is often the impulse response of a linear dynamical time invariant system, and h of n is the discrete time input signal. In that case, this convolution defines a response of the discrete time system to the input x of n. That is, the response of the system is completely determined by the impulse response and the input signal. Again, the impulse response is h and the input signal is x. In this form, this sum looks very abstract and complex. However, in practice, it's not. Let us write the first few terms of this sum. For simplicity, we will assume that x of n is 0 for negative values of n. If that's the case, we can write, or better to say, expand this sum like this. Y of n is equal to, let's see, since x of k is 0 for negative values of k, the sum will start from 0. And it will go up to infinity. And we have again x of k multiplying h of n minus k. And for k is equal to 0, we have x of 0 multiplying h of n. Plus, for k is equal to 1, we have x of 1 multiplying h of n minus 1. Then let's proceed. For k is equal to 2, we have x of 2 multiplying h of n minus 2. Then for k is equal to 3, we have x of 3 multiplying h of n minus 3, etc. The best approach for understanding a new mathematical concept is to immediately consider an example. And consequently, let's solve an example that will illustrate convolution sums. Here is the example. Our goal is to compute convolution of two signals given over here. That is, we want to compute this sum and we want to give a graphical interpretation of the convolution sum. The signals h of n and x of n are defined like this. Let's start with x of n. X of n is equal to 1 for n is equal to 0, 2 for n is equal to 1, 3 for n is equal to 2, and 0 for all other integer values of n. Here's a graphical representation of x of n. On the horizontal axis, we place a discrete time instant n, and on the vertical axis, we place x of n. For example, for n is equal to 1, the value of x of n is 2. Here's the definition of h of n. And here's the graphical representation of h of n. Now that we have this graphical interpretation of two signals, we can solve this problem. First, we will take into account the fact that x of n is equal to 0 for negative values of n. Taking this important fact into account, our convolution sum will look like this. Note over here that k starts from 0, that is, it doesn't start from minus infinity. Then, if we substitute the values of k in this general term, we will obtain this expression. Next, we need to take into account that x of n is not equal to 0 only for n is equal to 0, 1, and 2. And by substituting this important fact in this equation, we will obtain this equation. And consequently, we will only have 3 terms over here. In the sequel, we will refer to this sum many times, and consequently, let us write it down over here. We have y of n is equal to x of 0 multiplying h of n plus x of 1 multiplying h of n minus 1, and the third term is x of 2 multiplying h of n minus 2. Now let's compute this sum for different values of n. For n is equal to 0, we simply substitute n is equal to 0 over here, and we obtain x of 0, h of 0, x of 1, h of minus 1, x of 2, and h of minus 2. Now, let's look at this graph. We can observe that h of minus 1 and h of minus 2 are zeros. Consequently, we substitute 0 over here, and we are only left with a single term, x of 0 multiplying h of 0, and by substituting x of 0 is equal to 1, and h of 0 is equal to 3, we obtain 1 times 3 is equal to 3. Then, for n is equal to 1, this sum will look like this. We will have this term h of minus 1. h of minus 1 is equal to 0, consequently we are only left with the first two terms. And here they are. And by substituting the values, we have x of 0 is 1, h of 1 is 2, this term, then we have x of 1 is equal to 2, and h of 0 is equal to 3, this term, and the result is 8. Similarly, for n is equal to 2, we obtain this expression. Then, for n is equal to 3, we obtain this expression. For n is equal to 4, we obtain this expression. And that's it. In the sequel, we will give a graphical interpretation of the convolution sum, and we will explain how to compute this convolution graphically. To explain this, let's first analyze the derived equations. Here you can see the summary of the equations. First of all, in the sum terms, the position of the sequence x of n stays the same as n is increased. You can see over here, we have x of 0 over here, x of 1 over here, and x of 2 over here. On the other hand, in the sum terms, the sequence x of n is shifted in time at corresponding position in the sum. You can see it over here. We start from x0, x1, x2, x3, and x4. Then we have a shifted version over here, minus 1, 0, 1, 2, 3, and here we have minus 2, minus 1, 0, 1, 2. This means that in the graphical interpretation of the convolution sum, the sequence x of n is fixed and the sequence h of n is shifted. However, the sequence h of n has to be reversed or reflected with respect to the vertical axis. We will explain this in the sequel. For that purpose and for clarity, let us again write the general formula. Here it is. Next, let's expand this formula. However, this time we will keep both the values of n and k. For n is equal to 0, we obtain this expression. For n is equal to 1, 2, 3, and 4, we will obtain these expressions. Note over here that I keep both values of n and k in this sum. Note over here one very important thing. We have minus 0, minus 1, and minus 2. Basically, we have the sequence h of minus k. Then, what happens over here? We have this sequence h of minus k that's shifted for one time step. That is, we have 1 minus 0, 1 minus 1, 1 minus 2. Similarly, over here, we have the sequence h of minus k that's shifted for the 2 time steps, here for 3 time steps, and here for the 4 time steps. That is, in these sums, we can think of the sequence h of n minus k for n is equal to 0, 1, 2, 3, and 4 as the sequence h of minus k that is shifted or delayed for n time steps. Let us further explain how the sequence h of minus k is constructed from the sequence h of k, or equivalently h of n. Let us denote the sequence h of minus k by h1 of k. That is, h1 of k is equal to h of minus k. Taking into account the definition of the sequence h of n, for n is equal to minus k, the sequence h1 of k is defined like this. When k is equal to 0, h1 of 0 is actually equal to h of 0 and it's equal to 3. When k is equal to 1, h1 of minus 1 is equal to h of minus k, where k is now minus 1, and consequently we obtain this expression. For k is equal to minus 2, we obtain this expression. This is actually the original sequence h of n that is mirrored or reflected with respect to the vertical axis n is equal to 0. And here's the sequence h of minus k. If we delay or shift the sequence in time, we will obtain these sequences. Here they are. Let me zoom out for a second such that you can see them clearly. Here's the sequence h of minus k. Here's the sequence h of 1 minus k. That's basically the sequence h of minus k, only delayed or shifted one time step to the right. This is the sequence h of 2 minus k, shifted for 2 time steps. And this is the sequence h of 3 minus k, that is the sequence h of minus k, shifted for 3 time steps to the right. The previously explained analysis give us a graphical method for computing the convolution sum. And here is the graphical interpretation. We consider the case n is equal to 0. The first step is to reverse the sequence h of k to obtain the sequence h of minus k shown over here. Then, we only need to multiply the terms and to add them together that are inside of this dashed rectangle. In this case, we multiply this term by this term, we add them together to obtain this result. And that's it. Over here is the general formula. We are just computing this term. Here is a graphical interpretation of the convolution sum for n is equal to 1. What happens over here? We take the sequence h of minus k and we shift this sequence for one time step. As the result, we obtain this sequence. Then, the convolution for n is equal to 1 is computed like this. We multiply this term by this term. Then, we multiply this term by this term. We add them together, and that's the result. That is, we only multiply the terms that are inside of the dashed rectangle. Here's the graphical interpretation of the convolution sum for n is equal to 2. The procedure is the same. We take the sequence h of minus k, we shift the sequence for 2 time steps, and we obtain this sequence. Then we only multiply the terms that are inside of the dashed rectangle. We multiply this term by this term, this term by this term, this term by this term. We add them together, that is, we add the multiplication results together, and finally we obtain the result. That's it. And here is the general formula. The pattern is the same for n is equal to 3. Over here we shifted the sequence h of minus k for 3 time steps to obtain this sequence. Then we only multiply the terms that are inside of the dashed rectangle. We add the terms together, that is, we multiply this term by this term, this term by this term. We add the results together, and here is the result. Here's the graphical interpretation of the convolution sum obtained for n is equal to 4. Again, the sequence h of minus k is shifted for 4 time steps to obtain this sequence. And note over here our rectangle. The rectangle will only take into account these 2 terms. We multiply them together, and here's the result. And that's it. That was the graphical interpretation and the graphical method for computing the convolution sum. And finally, let's learn how to compute convolution in MATLAB. To do that, first we need to define 2 vectors. We define the vector x, representing the sequence x of n, here it is, and we define the vector h, representing the sequence h. Then we use the function convolution. We specify x, we specify h, and we specify this parameter full. This means that we will compute the full convolution. That is, we will consider all the cases. The output is given over here, and that's exactly what we computed before. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.